In this talk we present universal generative prior for image restoration. Given a degraded image, a regression network fails to recover realistic details. A generative network fails to maintain consistency with the input image. Our method, UGPNet, allows us to maintain the original structure of the input image and synthesize realistic details. Image restoration is a task that aims to recover the original image from unwanted degradations. Recent image restoration methods can be broadly categorized into two classes: regression method and generative method. Over the years, a range of diverse image restoration network architectures has been explored. Various network architectures have been proposed for each image restoration task. Regression methods directly map a degraded input image to a clean one using regression losses such as mean-squared error. These methods outperform in restoring accurate structures even in the presence of significant degradation. However, the regression losses lead to restored results that are close to an average of all possible realistic images. As a result, regression methods tend to produce blurry and unrealistic results compared to the original image. To tackle this challenge, generative methods using generative networks have been proposed. These images are generated using the popular generative network, style GAN. Generative networks have the capability to create textures and high frequencies similar to real images. Generative methods find significant application in tasks where synthesis ability is crucial, such as blind face restoration and super resolution. Generative methods embed a generator into their networks and inherit their ability to synthesize realistic details. They typically use an encoder to estimate a latent code from degraded input, then feed it to a GAN generator to create an image resembling the ground truth image. However, they suffer from limited representation power, which may cause the resulting image to deviate from the original structure of the input. Additionally, existing generative approaches rely on fixed network architectures tightly coupled with generative priors. Consequently, enjoying the rapid advances of regression-based methods within generative methods is challenging. We propose a novel framework, UGPNet, that combines the strengths of both methods. UGPNet integrates the precise restoration capability of regression methods with the realistic image generation ability of generative methods. As a result, UGPNet recovers accurate and high-quality images from degraded inputs. Our framework also offers great flexibility, allowing for the plug-and-play use of existing regression networks, making it applicable to various types of degradations. UGPNet consists of restoration, synthesis, and fusion modules. The restoration module recovers the original image structure exploiting an existing regression restoration network. The synthesis module then synthesizes high-frequency details by inverting and regenerating the restored image through a generative network. The fusion module combines the features from the restoration and synthesis modules to generate a final accurate, high-quality restored image. Here are the results of each module. The restoration module restores the accurate structure of the ground truth image, but it tends to generate images lacking in detail. The synthesis module produces realistically detailed images, but restored shape significantly differs from the ground truth image. Finally, through the fusion module, features from both modules are combined to generate the final accurate and realistic image. From now on, I will explain how each module is designed to achieve these goals. The restoration module utilizes an existing, pre-trained regression network to restore an accurate image. By adopting task-specific regression networks in a plug-and-play manner, it can handle various degradations. The synthesis module utilizes a pre-trained style GAN2 to generate perceptually realistic images. It takes the regression results as input, employing an encoder to estimate latent vectors. These vectors are then passed through the generator to obtain a realistic image. Lastly, the fusion module takes features from the preceding two modules as input. Through a carefully designed loss function, it recovers accurate shape and produces realistic texture from these features. The fusion module is trained with L1 and perceptual losses. However, due to misalignment, utilizing the result of the synthesis module through these losses becomes challenging. To address this issue, contextual fusion loss is applied. The contextual fusion loss calculates the average distance between the closest features in a patchwise manner and maximizes contextual similarity between images. This effectively resolves the misalignment issue in the synthesis module and facilitates the transfer of high-frequency texture from the synthesis module. We conducted experiments on 3 well-studied degradation tasks: denoising, deblurring, and super resolution. We applied degradations to the FFHQ dataset to create degraded clean image pairs for training. Similarly, we applied degradations to the Celeb AHQ dataset to create a test set for evaluation. Our framework supports flexible selection of diverse regression networks. Here are the results of deblurring and super resolution performed with different regression networks. These regression networks typically generate blurry outcomes. Our method successfully brings restoration power from the regression networks and combines it with a generative prior. Such flexible choice of regression networks allows us to easily equip existing and future regression models with our framework. We compare our method with recent restoration methods. The generative methods are unable to restore faithful image structures. The regression-based method failed to synthesize sharp details compared to the generative prior-based methods. In contrast, UGPNet succeeds in the faithful restoration and high-frequency synthesis of image structures and details. This is a quantitative comparison with other image restoration methods. In terms of FID score, UGPNet achieves the best scores, demonstrating its ability to generate perceptually plausible high-frequency details. In terms of PSNR and SSIM, UGPNet records higher scores than the generative methods, indicating structural consistency. We trained UGPNet on the LSUN Church dataset to validate its applicability on natural images. As shown in the results, UGPNet achieves more realistic high-frequency details compared to the state-of-the-art regression network. Although UGPNet combines a regression network and a generative network, it has a comparable number of parameters with others. In terms of inference speed, UGPNet is faster than computationally heavy models such as the transformer-based model and the dictionary-based model. Unlike other generative methods heavily dependent on the synthesis ability of the generator, UGPNet avoids introducing severe artifacts outside the training distribution of the generative prior. Thanks to the fusion module, it achieves faithful and natural-looking restoration. Here are limitations of our method. Although UGPNet is robust against failure of the generative prior, it may fail if the regression method fails. Also, UGPNet produces less sharp images than its backbone generative model, style GAN2, as it aims at higher fidelity results. We presented UGPNet, a universal generative prior framework for image restoration. Our method enables accurate restoration through the regression network and produces realistic results with a generative prior. The flexible framework allows the utilization of diverse regression networks, offering a plug-and-play approach for universal application across different degradations and networks. Our method demonstrates potential for integration with advanced regression networks in the future. Thank you for your attention.